Let's look at one aspect of the polymerase chain reaction. DNA is double-stranded, of course. The strands are anti-parallel. The primers come in pairs. The right primer and the left primer? How about the 5' to 3' primer and the 5, well, no, they're both 5' to 3'. How about the codon primer and the anticodon primer? Not really. Anyway, the primers come in pairs and they point toward each other in opposite directions. What if one of the primers has very poor efficiency? Let's see what happens. Separate the two strands. Let's put the poor primer here. It has a 5' and a 3' end. This primer has to fit well enough that the Taq polymerase can find it and bind and start the polymerization of the DNA. The polymerase is especially interested in the 3' end. Let's say that the 3' end has lots of GC pairs and that they're lined up and hybridized properly. The 5' end is not so good. The Taq polymerase can only start polymerizing about 10% of the time, but when it does start, it properly finishes the strand. The primer is like a catalyst. So now let's take this piece of double-stranded DNA. Let's just look at this strand and let's look at the primer in the other direction. This one works fine. Notice that it takes up the sequence that is complementary to the bad primer. That is the end of cycle 2. Cycle 3. Melt these and bring in the primers. But look, the primer that had trouble now finds a DNA segment that is perfect. Not surprising considering that the primer has defined its own complement. So by the third PCR cycle, the primers start making their own complement, and these are going to go into the exponential phase and become very real and visible amplicons. PCR experiments often produce unexpected extra stuff. Never forget that the ends of the amplicons are the original primers. A common trick is to put labels, fluorophores, on the primers to track them. This is part of DNA fingerprinting, a big PCR application.